Okay, hi guys. So we'll be continuing on seeing the relationship between the rate constants for a second order complex reaction. So we'll be seeing now for a second order complex reaction. Suppose we have a reaction like A plus 2B gives 3C, then the rate of reaction for this reaction would be Kr, which is the rate constant times A, the concentration of A and the concentration of B. Okay, and this we can write as minus dA by dt and minus half of dB by dt. So the rate of reaction is actually the rate of disappearance divided by the stoichiometric coefficient of the respective reactants. So stoichiometric coefficient for A was 1 and for B it was half. So we are just equating this with the rate constant and 1 upon 3 dC by dt. So we know that the rate of disappearance of A can be written as minus dA by dt, which can be written as, let's say, K1 concentration of A with concentration of B. Similarly, rate of disappearance of B can be written as again minus dB by dt, which can be written as K2 concentration of A multiplied with concentration of B. And similarly, we can write the rate of appearance of C can be written as dC by dt, or simply K3 A times concentration of B, concentration of A times concentration of B. So from the above equation, if you are just putting these values in this equation, then we can write that K1 would be equals to Kr, K2 would be equals to twice Kr, and K3 would be equals to thrice of Kr. Okay, for this particular case. Now let's have a look at another concept, which is integrated rate equations. We have integrated rate equations. First, let's focus on zero order reaction. So for zero order reaction, let's have a example. Suppose we have Ag going to form Bg plus Cg. So initial concentration was, let's suppose, A here and 0 and 0 here, and let's say concentration at time t was, let's say, we have A minus x here converted into x concentration of B and C respectively. So rate can be written as this is a zero order reaction, rate would be K times R. R would be equals to K times concentration of A raised to the power 0, and we can write that rate of reaction can be written as minus d a minus x upon dt would be equals to d of x upon dt. This should be equals to k 1 minus x raised to the power 0. So from here we can write that from these two equations we will get dx by dt as k. So we can write x would be equals to kt plus c. So we know that at t equals to 0, x is also equals to 0. So this means that c would be equals to 0. So this means that we would directly have x equals to kt as our final equation, where x is the concentration of product after time t. After time t. Okay, so in the next lecture we'll be continuing on from here, wherein we'll be drawing some of the graphs of the variation of x or the concentration of products with time, and we'll also be seeing how the concentration of reactants change with time. So till then, good luck and goodbye.